What is the statement of the theorem? What is the statement of the theorem? Right? This is the statement. What is eigenvalues of Hermitian operators are real? We want to understand the statement, then we will get proof easily. Some disturbance is getting. So I think okay, no one is there. Right. So we have to understand the statement, then only we will get solution or proof easily. Okay. Right. What is that means? Here two concepts are there. One is the eigenvalues, other one is the Hermitian operator. First, we want to know idea about the Hermitian operator. Right? Hermitian operator. So just see the statement, right? Right, coming back.
Sir, how it is calculated?
Yes.
How it is calculated?
It is calculated. No, what you are asking, just post in chat box.
This formula, I can't understand this.
That is a Hermitian operator and eigenfunctions, eigenvalues. Two concepts you have to know. So then it becomes very easy to prove the theorem, right? Okay, so once again, I am saying that Hermitian operator, what is a Hermitian operator, right? Just simply, I will show. So by using new slide whiteboard, right? Right. So here you have to remember the concept of Hermitian operator and eigenfunction and eigenvalues. First thing, operator A is there. This is A is an operator. When we called the operator A is a Hermitian operator. A is a Hermitian operator. For that, we have to choose one wave function, that is the psi. We are going to choose the wave function psi, and its conjugate wave function becomes what? Psi star. The conjugate wave function of the psi becomes what? Psi star. These are the parameters are there. So first what you should do means keep psi star constant. Psi star should be kept constant. Then the operator A operates on this wave function psi. That means write operator A and the function psi. Right? Psi star kept constant. The operator A operates on psi and doing integration within the limits. What you get the result, that should be equals to, now this time kept constant psi. Psi becomes kept constant. Then the operator A operates on psi star. Right? So that means operator A operates on the psi star, A into psi star, then doing integration within the limits. These two results becomes the same. So means in first condition, what we get the result that should be similar to this second condition. Therefore, we can say this particular operator is called a Hermitian operator. Is called a Hermitian operator. Is it clear?
Yes, sir.
Yes. Then
Yes, sir.
we want to know some concept of eigenfunctions and eigenvalues, right? So same operator, same wave function, that is the psi, right? The operator will be same and the function will be same. How we can define the properties of the eigenfunctions and eigenvalues? Simply the operator A operates on the wave function, right? Psi. We will get a same wave function. We will get a same wave function, but multiplied with some constant value, that is the lambda. So this is called eigenfunctions and eigenvalues concept, right? So we are going to apply these two conditions, then we will get the solution of the theorem 1 easily. Is it clear?
Okay, sir.
Yes, sir.
Yes. Okay. So now we'll see our theorem, right? Right. Is it visible to you?
Yes, sir.
Yes, sir.
Yes. Just see the theorem, right? So what it explains. Consider operator is A and wave function, that is a psi of x. Simply apply eigenfunction concept. Operator A operates on psi. We will get lambda 1 into psi. Okay. Lambda 1 is the eigenvalue. Lambda 1 is the eigenvalue, right? Now consider conjugate wave function of this psi. That becomes what? Psi star. Psi is there. Now we are considering psi star. The same operator operates on psi star. That will give another eigenvalue, that is the lambda 2. Right? Is it clear up to here?
Yes, sir. Yes, sir.
Yes, sir.
Yes. Now what we are going to do, right? So we know the Hermitian operator definition. That's why here psi will be there in equation 1. This will be multiplied with psi star. Where psi function will be there, we are going to multiply it with psi star. In the second equation, psi star is there. We are going to multiply it with psi. That is the thing only, right? After multiplying, both functions are integrating within the limits, right? For example, here, this is the function will be there. This is multiplied with psi star means just write simple psi star in front of A into psi and integrate within the limits, that is the d tau. Similarly, psi star will be right in front of lambda 1, right? So then do integration. So that is the equation 3 only. In equation 2, psi will be there, means psi star is there. We are multiplying psi means here multiplied with psi and do integration. Here multiplied with psi and do integration. So right. So what we are getting the LHS, that is the left hand side, these two are becomes equal because operator is a Hermitian operator. Therefore, we need to equal the right hand sides, then we will get the result. That is the thing. Okay. Right. So that we are going to see the slides, right? To see the equations, what are there. Right. So just see. Here equation 1 will be there. This will be multiplying with the psi star only, right? Multiplying with psi star means here getting equation. That is psi star into A into psi is equals to psi star into lambda 1 into psi and integrating both sides. That is the integral within the limits, that is the dt, right? Small limits we are utilizing, that's why dt, integration dt, right? So then we'll get equation number 3. What was that equation number 3, right? This is the equation. Integral of psi star into A into psi into d tau is equals to lambda 1. Already we told that is a constant one. That's why take front side. Then integral of psi star into psi into d tau. That is the equation number 3, right? So here we got one equation. That is the equation number 3. Then another second equation will be there. What is the second equation means? This is the second equation. A into psi star is equals to lambda 2 into psi star. But we are going to multiply it with psi and integrate on both sides. Just simply multiply with psi on both sides and integrating. We will get equation number 4. See equation number 3. This is the equation number 3, not the previous one, right? Because this is also same, but lambda 1 here we wrote front side. Okay. From equation 3 and equation 4, just see these two equations. According to Hermitian operator, this one is equal with this one, right?
LHS equal to RHS.
Yeah, these both are equal whenever the operator is a Hermitian operator. If we say operator is a Hermitian operator, then these two are equal. Therefore, simply we are going to equal these two, right? See, lambda 1 into integral of psi star into psi into d tau is equals to lambda 2 into integral of psi into psi star into d tau. So that is the equation we are going to see right hand side, right? So just I will show that equation. Right. So what is that equation means? So just see here. So this is after equaling RHS, lambda 1 into integral of psi star into psi into d tau is equals to lambda 2 into psi star into d tau. If the wave function psi becomes a normalized wave function, means integral of psi into psi star is equals to 1, or else psi star into psi is equals to 1. Therefore, these two are becomes 1. So therefore, we will get lambda 1 is equals to lambda 2. What is that means? If operator is a Hermitian operator, we will get a same eigenvalue. We will get a same means lambda 1, lambda 2 both are same means we will get a same eigenvalue. Whether the function may be normal wave function or its conjugate wave function, whatever it, we will get a same eigenvalue. That's why we are going to conclude the eigenvalues of Hermitian operator are real. Means the both are equal, right? Yes, is it clear?
Sir. Yes, sir. Yes, sir.
Yes, sir.
Yes. Okay. Now the another theorem will be there. So we'll see the second theorem. You people may try to understand what is the statement of the theorem. So therefore, we will get the solution easily. If you cannot understand this theorem, then how can you do proof, right? Proof of this theorem, that is too difficult. Whatever it question will be there, first we need to understand that question. Then, so we go through the simple manner how we'll get the solution of that question, right? So see, one more theorem will be there. So just we discuss about the statement of the theorem. If psi 1 and psi 2 are the two wave functions, previously we have only one wave function, right? Here two wave functions are there, that is the psi 1 and psi 2. These two wave functions with different eigenvalues on Hermitian operator. Operator is the Hermitian operator only, but two functions are there, the two functions with two different eigenvalues. Whenever the two functions with different eigenvalues, the operator operates on these two functions. The two functions must be orthogonal to each other. Then the eigenfunction, the two eigenfunctions are orthogonal to each other. What is the orthogonal to each other function means? Simply orthogonality rule means here two wave functions are there, that is a psi 1 and psi 2. The integral of psi 1, psi 2 into d tau. The integration of psi 1 into psi 2 into d tau is equals to what? 0. We are going to prove this one. That is the statement of the theorem, right? So what the statement may explains what we are going to prove. We need idea about this. So then we will get the solution by applying same concept again, eigenfunctions and eigenvalues and Hermitian operator. The procedure was same, but the representing phenomena was different, right? See, this is the statement of the theorem. So I think all of you understand the statement of the theorem, then only you will get the solution easily, right? Two wave functions with different eigenvalues, but in this time, the operator operates on the two functions. The two functions must be orthogonal to each other. So we'll see whether the two functions are orthogonal to each other or not. This is the we are going to prove, right? So for this, what we are going to do, we'll see. Right. Just simply see the proof, right? Right. Consider a Hermitian operator, right? Here, what is A is an Hermitian operator. Same terminology here we use. A is a Hermitian operator. Psi1 and Psi2 are the two wave functions with different eigenvalues, means lambda1 and lambda2. Okay. Simply the operator A operates on Psi1. We'll get this equation number 1. The operator A operates on the second wave function. We'll get one more equation, right? This is the equation number 1 and this is equation number 2. Is it clear up to here? Is it clear?
Okay, sir.
Yes, sir.
Yes. Single operator is there. Two wave functions are there. If the operator operates on one wave function, we'll get one eigenvalue. That is the lambda1. If the operator operates on another wave function, we'll get another eigenvalue. That is the lambda2. Right? These are the two equations. So when we know these two equations, right? Wherever psi1 will be there, now we are going to multiply it with psi2. Psi1 ఉన్న equation ని దేనితో మల్టిప్లై చేస్తున్నాం? psi2 తో మల్టిప్లై చేస్తున్నాం. మల్టిప్లై చేసి వదిలేస్తున్నామా? ఇంటిగ్రేషన్ కూడా చేస్తున్నాం. Within the limits d tau. Similarly, equation 2 will be there. So that it will be multiplied with psi1 and do integration within the limits. Okay. So the same thing previously psi and psi star are there. Here psi1 and psi2. So the procedure and approaching phenomena was same only, right? So these are the two equations are there, right? So these are the two equations. That is a into psi1 is equals to lambda1 into psi1. A into psi2 is equals to lambda2 into psi2. See, equation 1 is multiplied with psi2 and integrate. So దీన్ని ఏం చేస్తున్నాం చూడండి, equation 1 here psi2, then here psi2 and also integrating. We will get this one. Psi2 a into psi1 into d tau integral is equals to integral of psi2 into lambda1 into psi1 into d tau. Here we take common lambda1. Okay, here we take common lambda1. Similarly, equation 2 will be there. What is that? Equation 2 will be there. Equation 2 multiplied with psi and integrating within the limits, right? So we will get one more equation. So in that equation 3 and equation 4, we will get a Hermitian operator definition. So that means left hand sides are equal. Therefore, we need to equal the right hand sides, right? Here,
Yes, sir.
Here directly we wrote this because after this equation 3, we will get equation 4. What was that equation 4 means? Here I will write, just see. Integral of, right? Integral of, this is the equation multiplied with psi1. Psi1 a into psi2. Psi1 a into psi2 into d tau is equals to, what will get? Lambda2 will be there, na? Lambda2 kept constant outside, integral of psi2 psi1 into d tau. Psi2 psi1 into d tau. So this is the thing we will get. So see this one, this is equation number 4. This one and this one both are same. According to Hermitian operator, these two are same. Therefore, we are going to equal these two. That is lambda 1 and
LHS.
lambda 2. Therefore, RHS means this is the equation we will get. Okay.
Yes, sir.
The same procedure phenomena what we did previously. Okay. So then, so this is the equation we'll get. What we are going to do means, right. So simply the right hand term will be considered to the left hand side. So that means the previous equation was lambda 1 into integral of psi 1 psi 2 into d tau is equals to lambda 2 into integral of psi 1 into psi 2 into d tau. So now we are taking left hand side and equals to 0 means lambda 1 minus lambda 2 integral of psi 1 into psi 2 into d tau is equals to 0. But from the previous experiment, we know that lambda 1 and lambda 2 is not equals 0 because here different eigen values are there. Lambda 1 and lambda 2 are different. We are saying in the statement itself. Whenever these two are different means not equal, right? So therefore lambda 2 minus lambda 1 becomes not equals to 0. The two are different. We won't get 0 by subtracting of lambda 1 and lambda 2. But here the overall result becomes 0 means it must be equals to 0. This is not equals 0, but result is 0. So means this term becomes particularly equal to 0. So therefore that is integral of psi 1 into psi 2 into d tau is equals 0. So therefore we can say that the wave functions are orthogonal to each other. Therefore the wave functions are orthogonal to each other. Is it clear?
Yes, sir.
Right. So try to understand that terminology, right? So how we are going to get the solution of theorem. Okay. Right. Last theorem will be there, right? Right. That is the theorem number 3. So we'll see what is the theorem 3. So this will be related to the commutation property, right? What is the statement of theorem 3? Check out commutation of eigenfunctions. Here we need to know definition of the commutation property and eigenfunctions definition, right? So what is the eigenfunction and what is the eigen operator and what is the commutation property, right? Right. See, the A and B are the operators and psi is the wave function. Whenever we are going to conclude the commutation property, two operators are required. So remember that two operators are required. The two operators are A and B are the operators. A and B are the operators. And psi is the wave function. So then the two operators are involved in commutation property. Therefore, we can say A into B into psi is equals to B into A into psi. What is the meaning? Means if operator B operates on this wave function psi, we'll get some result. Again, the operator is apply on that result, we'll get another new result. That should be equals to when the operator A operates on psi, later the B operates on that result. We will get same result. Therefore, we can say the both operators A and B are operators are commutation with each other. Okay. So that is the definition of the commutation property. By applying eigenfunction concept, we are going to check the the eigenfunction will be involved in commutation property or not with respect to the operators, two operators A and B, right? So definitely the eigenfunction becomes involved in a commutation property that we are going to prove. Okay, right. So for that, what we should take, right? The wave function psi can be defined as the linear combination of atomic orbitals. So this is the commutation property A into B into psi is equals to B into A into psi. A into B into psi is equals to B into A into psi. That is a commutation property. For that, we are choosing one wave function that is a psi is the linear combination of atomic orbitals. Psi 1, psi 2, pi. This is the pi. Pi 1, pi 2, pi 3 and pi I are the atomic orbitals. The linear combination of these atomic orbitals, which will be with the linear coefficient C1, C2, C3 and Ci. Or else we can written as psi of x is equals to, we can written as psi of x is equals to summation of Ci pi I into x. This is the psi we are going to select. So then this psi becomes a eigenfunction. We are going to prove that, right? Okay. So we'll see how this function, how this chosen wave function becomes a eigenfunction. We'll see. According to this condition, what condition? Commutation property condition, right? According to commutation property, what? A into B into psi of x. Here psi we have this one. Now first what we should do? Operator B is operates on this function. Later operator A is operates on this same function. Okay, means what will get the result. That is the thing we are going to do, right? Just simply see left hand side we are considering, right? Yes. Are you able to see this? A into B into psi of x? Yes. Are you seeing this?
Yes, sir.
Yes. A into B into
Yes,
psi
sir.
of x. This is a psi of x. We are going to apply these two operators on that wave function. That is A into B into psi of x. First, the operator B is operates on this function. We'll get same function. We'll get same function with eigenvalue. That is the small bi is the eigenvalue. Clearly understand. The operator B is going to operate on the wave function that is the psi. So it is the eigenfunction. That's why we will get some eigenvalue. That is the eigenvalue is the bi. Bi into psi we will get. That is a bi into this is the same psi. Okay. Now bi is the eigenvalue. That's why kept outside. Again, the operator A is operates on that wave function. We will get one more eigenvalue, that is the AI. Therefore, finally, A into B into psi of x is equals to AI, BI, CI into pi of x. This is the equation, right? Simply, operator B is operates on the wave function. We'll get eigenvalue, that is the BI, with the same function. Again, the operator A is operates on this function. We'll get one more eigenvalue, that is the small ai. Therefore, ai into bi and function was ci into pi of x. That is the result we will get. Okay. Now, similarly, what is b into a into psi of x? We are going to do that is b into a into psi of x. B into a into psi of x. Right? B take outside, the operator A is operates on this wave function. We will get one eigenvalue, that is the AI. So just keep side AI. and B operator is operates on this function, will get BI, right? Will get BI. So therefore, these two are equal because finally we will get the result whether A is operates initially or B is operates initially. Will get same result. Therefore we can say the operator, right? So this is the result second time we are getting. So therefore, from equation 1 and 2, we can say A into B into psi of x is equals to B into A into psi of x, right? So hence the eigenfunctions are shows a commutation property. The eigenfunction shows a commutation property, right? So this is the proof of the third theorem, right? So once again we are going to conclude that theorem 1, theorem 2 and theorem 3, right? So theorem 1, theorem 2 and theorem 3. So just see. Right. Just see. This is the theorem 1. The eigenvalues of Hermitian operator are real. Means if you consider different eigenvalues, it will be shows that both are equal. That is a theorem 1. Now in the second time, consider that this is a second theorem, that is psi 1 and psi 2 are the two wave functions with different eigenvalues. Here we are saying eigenvalues are different and operator A is Hermitian operator. Therefore, we can say the eigenfunctions are orthogonal to each other. What are the two functions are there? The two functions are orthogonal to each other. That is a condition we are going to show, that is integral of psi 1 into psi 2 into beta is equals to 0. So that is the proof of the second theorem. So then another theorem will be there. So that is about commutation property, right? So here we are going to do, so that is the commutation property of eigenfunctions, right? So check out the commutation property of eigenfunctions means the two operators are operates on eigenfunction. So that will be the two operators will be commute to each other. So that is the theorem number 3. 3 theorems are important for exam point of view. Don't skip any theorem. You have to read all those 3 theorems carefully, right? So and one more important topic, that is derivation of the Schrodinger wave equation. The derivation of Schrodinger wave equation. Actually, it is very simple to understand. So, but somehow numericals will be there. You have to concentrate on that, right? Otherwise, it will be very difficult. And also remember, the further topic, the further entire topic that should be depends on this Schrodinger wave equation only, right? If you understand that Schrodinger wave equation, so it will be easy to understand the further topics, right? So much concentrate, just 10 to 15 minutes enough to complete this derivation part, right? You people may concentrate, right? Overall, I will be conclude So this Schrodinger derivation simply, right? We are saying according to de Broglie principle, whenever the electron which will be revolving around the nucleus, that will be possess dual nature. One is the particle nature and the other will be the wave nature. One is the particle nature, the other will be the wave nature. So the wave motion that will be depends on x and t. This is the first postulates of quantum mechanics. Already we discussed that what is the first postulate of quantum mechanics means the wave function, whatever is the wave function we are going to choose, that should be depends on axis and time, or that should be variable with axis and time, right? So here, so we consider a stretched string, right, or any vibration of the object at that time. So this wave motion will obtain whenever the object will be present in vibration, right? So at that time, so that wave may possess a second order differential equation. So that second order differential equation be this one. Dou square W by dou X square is equals to 1 by C square into dou square W by dou T square. Here C is the velocity and W is the motion of the particle, right? So simply here what, according to de Broglie, the particle which will be moving, right, which will be moving, that may possess wave nature and particle nature, right? So the wave nature means the second order differential equation for that wave motion, that should be written as like this: dou square W by dou X square, then is equals to 1 by C square into dou square W by dou T square. Two functions are there, right? So you must concentrate. One is the X and other one will be the T, right? So two functions will be there. One is the X and other one will be T, right? So this is the equation, just you may see. Dou square W by dou X square means X variables are there. 1 by C square means that will be depends on the velocity. And dou square W by dou T square means time factor will be there. The wave function psi that should be depends on X comma T. That is the first postulates of quantum mechanics. So that's why the second order differential equation can be written as like this, where W is the motion of the particle that is depends on X and T. So that's why we are going to define W. W is equals to F of X into G of T. Means the W, that is a wave motion that can be defined with the help of variables, that is X comma T. These two variables are there. X means we may call as F of X. T means G of T, right? So and the G of T, the time dependent function can be written as G of T is equals to A sine 2 pi gamma T. A sine 2 pi gamma T. So means G of T means the time dependent factor that can be defined as, that is with respect to the sine function. You need to remember these three equations, then you will get the solution. That is simple. Okay. So a little bit concentration is required. So this is the second order differential equation, right? This is the second order differential equation. Here W will be there. So that is, we are choosing F of X into, this is not minus, F of X into G of T. So then G of T can be defined as A into sine 2 pi gamma T, right? So now simple differentiation will be there. So what is the differentiation? 2 times differentiation. This is the equation. We are going to substitute the terms in that first equation, right? So means W will be there. we are going to differentiate W with respect to X 2 times. Again, W will be there. We are going to differentiate with respect to time 2 times. Then what you get the result? That result will be substituted in this equation. We will get Schrodinger wave equation. Yes, are you people understand the concept?
Yes, sir.
Clear గా వినండి. కొంచెం కాంప్లికేట్ అనిపిస్తుంది, but that is too easy to understand, right? Second order differential equation is there. W we are going to define. Now what we should do means this W should be differentiated with respect to X 2 times. What you get the result that will be substituted here. Again the W will be differentiated with respect to T 2 times, double differentiation. What you get the result that will be substituted here. So therefore we will get the Schrodinger wave equation that we are going to do further. Okay. So then that will be C simply. Right. Yes. So just see, are you able to see this? Right.
Yes, sir.
So finally the W can be defined as f of x into g of t. G of t we have defined that is a into sine 2 pi nu t. This is the g of t. This is the f of x. That is the W. What we are going to do means we are going to differentiate with respect to time. Time to differentiate చేసినప్పుడు f of x is kept constant, right? In entire equation f of x becomes constant because we are going to differentiate with respect to time only, right? Okay, here in the second term time will be there. We are going to differentiate this. One time differentiation means sine becomes cos. In place of x, this entire equation will be there. That's why we will do again differentiation of this 2 pi nu t with respect to time. We will get 2 pi nu. Okay. So therefore, dou w by dou t is equals to f of x into a into 2 pi nu into cos 2 pi nu t. Again, one more differentiation, that is the double differentiation, right? So a kept constant, f of x kept constant, then 2 pi nu kept constant. The cos differentiation becomes a minus sine 2 pi nu into t. In place of t, 2 pi nu will be there. Again, we will get 2 pi nu. So therefore, finally, we will get the result that is minus 4 pi square gamma square into a into sine 2 pi nu t into f of x. This is the equation, that is dou square w by dou t square. Yes. Now the w is equals to f of x into g of t. We know that. Now we are going to differentiate with respect to x, right? So here small mistake will be there. That is the dou square w by dou x square. Here g of t kept constant. G of t kept constant. Now we are going to double differentiate of w, that is dou square w by dou x square is equals to dou square f of x by dou x square into g of t. This is equation number 5, right? Now these two equations, equation 4 and equation 5 are substitute in equation 1. What is the equation 1? I will write here, just see. Dou square w by dou x square. Dou square w by dou x square is equals to 1 by c square into dou square w by dou t square. This is the equation number 1. That is the second order differential equation for wave motion. Now equation 4 will be substituted here and equation 5 will be substituted here. Then simplifying, we will get this Schrodinger wave equation. Okay. Is it clear? Just see, clear cut.
Okay, sir.
Okay. Just differentiation w is there. We are going to define w in the form of f of x and y, g of t. 2 times differentiation we are doing. With respect to t 2 times, with respect to x 2 times. That values are substituting in this equation. After substitution in this equation, we will get one new equation. That new equation will be simplified. We'll get a Schrodinger wave equation, right? So that is the thing we'll see left hand side, right? Right. So therefore, substitution of these two equations, right? We will get one new equation, that is in equation 1, if we can substitute dou square f of x by dou x square into g of t is equals to minus 4 pi square gamma square by c square into a into sine 2 pi nu into t into f of x. This is what a into sine 2 pi nu is equals to what? G of t. This is already we defined g of t. Therefore, right hand side g of t will be there, left hand side g of t will be there. That will be cancelled. This is cancelled. Therefore, dou square f of x by dou x square is equals to 4 pi square. Here, c square by, right, nu square. Nu square by c square is equals to what? Lambda. Lambda is equals to c. Nu is equals to c by lambda, right? So just see the definition of nu is equals to c by lambda. Here are there. So then nu square is equals to c square by lambda square, right? So therefore lambda square is equals to what? We can write c square by nu square. But here nu square by c square will be there. That's why we will get lambda square in denominator. So therefore, instead of nu square by c square, we can write lambda square. So this is the equation we'll get. Therefore, in that lambda, from de Broglie equation, we can substitute the lambda. We'll get what we are trying to get the equation, that is a Schrodinger wave equation. Okay, right. So that is this is the equation, right? So simply, so this is dou square f of x by dou x square is equals to minus 4 pi square by lambda square into f of x. But according to de Broglie equation, lambda is equals to h by mc or h by p. Therefore, lambda square is equals to h square by p square. In case instead of lambda square, we are going to substitute h square by p square. So that becomes dou square f of x by dou x square is equals to minus 4 pi square p square by h square into f of x. But we know the kinetic energy is equals to half mv square, and total energy is equals to kinetic energy plus potential energy. Total energy is equals to kinetic energy plus potential energy. So therefore the potential, the kinetic energy can be written as E minus V, means total energy minus potential energy. So this is some simple simplification is there. This is the total energy, kinetic energy plus potential energy. Kinetic energy is equals to total energy minus potential energy. E minus V is equals to kinetic energy means half mv square. That is, when 2 comes left hand side, 2 into E minus V is equals to mv square. Now multiplied with m on both sides. That is 2 into m into E minus V is equals to m square V square. Due to m square V square is equals to p square. Therefore, in the previous equation, the p square value will be substituted. We'll get this equation. That is, dou square f of x by dou x square is equals to minus 4 pi square by h square into 2m into E minus V into f of x. So by multiplying of these 2m, we will get minus 8 pi square m by h square into E minus V into f of x. This will become left hand side, that is dou square f of x by dou x square plus 8 pi square m by h square into E minus V into f of x is equals to 0. This is the Schrodinger wave equation. So generally, in case of f of x, if we may use psi, that is dou square psi by dou x square plus 8 pi square m by h square into E minus V into psi is equals to 0. So that is the Schrodinger wave equation. in terms of x-axis only. If it will be applicable for three-dimensional system, right? Three-dimensional system. So we can write that Schrodinger wave equation, that is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into e minus v into psi is equals to 0. E minus v into psi is equals to 0. This is the Schrodinger time independent equation, time independent wave equation, right? Is it clear? Somehow difficultness is there. So you people may practice that equation. Definitely you will get the solution easy. Okay. Right. So further the remaining topic we are going to discuss in the next class. Okay.
Excuse me, sir.
Yes, tell me.
This Schrodinger wave equation comes for the 10 marks question, no, sir?
Yeah, 10 marks question.
Okay.
There is a scope to ask 10 mark question, postulates of quantum mechanics and Schrodinger wave equation derivation.
Okay, sir.
Out of these two, one question definitely will be there in the examination.
Oh, sir.
Right?
Thank you, sir.
Okay. I already sent these notes to you, right? If any doubts will be there, you may contact on WhatsApp. Okay?
Okay, sir.
Right.
Sir, number is there in the group, sir? Your number is there in the group?
Yeah. My number is there. Okay?
Okay, sir. Thank you.
Right. So I am going to conclude the class, right?
Sir, assignment lo one question
hydrogen atom.
Assignment, sir. Assignment question.
Assignment question hydrogen atom undi. Next ade manam cheppedi. Particle in one dimensional box and a hydrogen atom. Right?
Adi
చెప్పండి.
అది polarography అదొక డౌట్ వచ్చింది సార్.
Polarography, okay, you may
yes sir.
You may write polarography from the book only, right?
Okay sir.
మీ బుక్ లో నుంచి చూసి రాయండి అసైన్మెంట్.
Okay sir. Okay sir.
Okay.
Thank you sir.
Further topic we will discuss tomorrow. Okay. Okay, now I am going to conclude the meeting. Yes, all of you take your dinner and take care. Bye.
Sir.
Yes.
Notes Telegram లోనే పెడుతున్నారా?
పెట్టాను ఆల్రెడీ నోట్స్ ఎప్పుడో లాస్ట్ వీక్.
ఓకే సార్. రాలేదు సార్ అయితే.
రాలేదు అందుకని.
సరే ఎవరైనా ఒకరు మెసేజ్ పెట్టండి నాకు పర్సనల్ గా నేను షేర్ చేస్తాను.
ఈ నెంబర్ కి పెట్టాలా సార్ మెసేజ్?
నా నంబర్ కి పెట్టండి.
ఓకే సార్.
నేను షేర్ చేస్తా, మీరు గ్రూప్లలో పెట్టుకోండి. ఓకే.
ఓకే సార్, థ్యాంక్ యూ.
Sir.
Yes.
Today's notes you didn't send, sir.
Yeah, I will send.
Okay, sir.
Okay, fine.
Sir, మీ నెంబర్ లేదు సార్ మా దగ్గర.
My number?
Yes sir.
టెలిగ్రామ్ లో లేదు సార్ మీ నెంబర్.
Acha.
Number.
Just note down my number. I will send in this chat box.
1 minute, sir.
Just open chat box. My number is there.
Wait, sir. Wait. Chat box open.
Yes. Got it? Chat box open chesara?
Yes sir, yes sir.
My number is there. Okay. Right. Whatever is the question, queries are there. We will discuss in tomorrow's class. Tomorrow class is there, na?
Yes sir.
Yes. You people may take care and have your dinner. I'm going to conclude the meeting.
Hello, excuse me, sir.
SS.
Sir, maths class also you only take, sir.
No. Only physical chemistry.
Sir.
Yeah, only physical chemistry. Okay.
Thank you, sir.
Okay. Bye.
Good night.
ସରିଗଲା